Hi, today I'm going to be talking to you about our work in the area of decision support systems for improving emergency response. This work has been sponsored by the National Science Foundation and the Tennessee Department of Transportation over the last 6 years. Emergency response is a critical service that is managed by the safety agencies in our cities. They respond to incidents that include situations such as fire, cardiac arrests, and motor vehicle accidents, in addition to several other categories. The challenge for the communities is to be able to provide efficient response with limited resources. The problem is very challenging because these agencies often must cover large areas of service across a geographical region, and the time spent in travel often leads to delays in response. In the last few decades, principal data-driven optimization has helped optimize emergency response. One way to tackle the complex problem of emergency response is to dynamically plan the availability of resources in a given region. In a way, this becomes an adaptive planning problem where we first estimate the likelihood of events across the region and then reposition the resources in anticipation of such incidents. The second aspect of the approach is to perform early detection of the incidents and then dispatch resources to the scene of the incident. Computationally, this becomes a predict then optimize problem where the prediction problem requires us to learn a function f over some measure of incident occurrence x, such as the frequency of incident occurrence, conditional on w, and some parameters theta. W denotes features of interest. The decision problem is to find a policy that enables the selection of an action that maximizes the objective g, which is typically expected response time. Our group has solved this complex problem using a four-step approach. By developing principal forecasting models, by developing decision procedures for resource allocation even under non-stationary conditions, by ensuring that we are building decision procedures that are robust to the lack of information and communication failures, and developing a principal framework for early detection of incidents. These components have been integrated into a tool chain called Statistical Response Toolchain, or StatResp for short. Before going further, it will be prudent to point out some of the challenges in the state of the art and some of the challenges that we have not yet solved. This information has been summarized in a survey paper that we recently wrote. The paper discusses the state-of-the-art approaches in forecasting, detection, and decision-making. Crucial challenges include the problem of scale, specificity, and high granularity in space and time. While many models work at the 4 to 6 hour temporal resolution and use coarse spatial discretization, first responders often need 30-minute to 1 hour forecasts at the level of city intersections or blocks. Further, many approaches, including ours, still find it challenging to forecast the severity of incidents. The problem stems from the sparsity of incidence data. Similarly, a massive challenge in decision-making is the challenge of non-stationarity and changes in the environment. Let me now talk about a few ways in which we have tried to solve these challenges. We first start with the detection problem based on our recent ICDM-21 paper in collaboration with Professor Hemant Purohit from GMU. Our approach takes crowdsourced data from Waze and uses a small unit temporal and spatial window and subsequently convolutional neural networks to identify the likely location and time of real incidents. The challenge is that crowdsourced data is itself imprecise. We then use Pareto optimization to balance parameters that are important to first responders rather than merely focus on accuracy. We've also been working on density learning approaches to learn the distribution of traffic flow across the region and then identify correlated spatial and temporal anomalies using the current observation and the learned density of past traffic observations. Such severe anomalies are often the indication of a traffic incident. We have been able to show that this approach complements the Waze approach and provides a framework for early detection of incidents even before they have officially been reported. Next, let me talk about our work in the area of forecasting. We use a combination of clustering and synthetic resampling to reduce the imbalance between classes of data rows with incidents and data rows without incidents. Thereafter, different approaches like neural networks and survival models can solve the challenge of forecasting. Clustering lets us balance model heterogeneity with variance. The figure on the top shows the predicted incidents in Nashville in January 2019 on the left and the real incidents on the right. In a paper at ICCPS 2019, we also showed that such models can be updated online if they are required to ingest more data. Finally, I would like to discuss the problem of decision-making, which, as I mentioned earlier, involves adaptive planning. In our work, we have shown that there are actually three different approaches that practitioners can take. First, to your extreme left is a completely centralized approach to planning, which usually does not scale for large environments. The second approach, to your extreme right, is a completely decentralized approach, and the approach in between uses hierarchical planning. For all three approaches, our basic formulation involves a semi-Markov decision problem. A massive challenge is that the transition function cannot be estimated in closed form. Also, the state and the action spaces are often intractable in practice. One way to scale these planning approaches is to use hierarchical planning. Essentially, we use a two-step approach. In the first step, by using a high-level planner, we segregate the overall decision-making problem into smaller sub-problems. Then the smaller sub-problems can be solved in parallel. To solve the smaller sub-problems, we use Monte Carlo tree search and a generative incident prediction model, thereby bypassing the challenge of not knowing the transition functions in closed form. Now, let me point out how these planning approaches can work under limited communication. One way to tackle limited communication between agents is to use completely decentralized planning or partially decentralized planning, where instead of using a monolithic state space, we let each agent focus on locally available information. Advantages of this approach are that it scales really well, even as the number of agents increases, and it's resilient to communication failures by construction. A disadvantage is that it requires many assumptions regarding agent behavior and can lead to suboptimal decision-making in comparison to a completely centralized approach. We have evaluated and studied our methods in collaboration with the Nashville Fire Department and the Tennessee Department of Transportation. A recent study showed that our approach can help reduce response times by close to 20%. The figure shows a dashboard that we built for our partner agencies. Finally, let me conclude by mentioning that there are still open challenges in this domain. For example, forecasting incident severity remains a massive challenge. In addition, we need to look beyond the standard metrics such as response time optimization and improve multi-agency coordination, which is a source of inefficiency in practical decision-making. Thank you.